And the trial with 1 million episodes ended, and it went good, I would say. So again, epsilon decay not really important here. The path, that is strikingly evident that the most exploited path is one of the optimal paths. Now the reward is smoother. Okay, 1 million episodes, now the reward is much smoother. There is lots of variations. Again, we kept the original parameters, so 0.05 exploration. But this plot tells us that at the end of training, we almost always get to the goal. And in testing, this is our actual optimal policy. The testing episodes are gone now. I can't post them, but yeah, a reasonable policy has been achieved. Obviously, you can go back. What else you can do? Whatever you want, basically. So, for instance, you can go back to the original map, more or less 0.1, 0.9, maybe a bit less of exploration if you want. And, for instance, try to increase the number of frozen tiles. Be careful, because sorry, I need to fix this. Okay, now it's a bit more difficult to get to the right path. And in fact, I think it failed. Okay, it almost always crashes somehow. So you need much more time. The environment is much more complicated, even with this slight variation. Let's see. 0.1, 0.9, 0.5. Well, that's good. Let's try with more. And then if you want to go even more complex, you can put the parameter is slippery to true. That will be even more difficult, because I don't remember the exact mechanics to be honest. I will need to check, but yeah, the ground becomes slippery. So I guess that at each decision step, in place of the action you have chosen, the previous action could be chosen. It should be like this. No, even this time we didn't succeed. We explored too little. We got some time to the reward, but very seldomly. And in fact, we didn't learn. Yeah.
I didn't understand the 10 part that we see at the end, the animated part.
That's we froze the last Q table that the agent had.
Okay.
And we use that Q table without exploration. So we stick with that Q table.
For 10 times?
Yeah, just to see what happens. We could do one time, but one time is too quick.
If we froze it, isn't it supposed to be always the same?
Yeah, it should be always the same, unless there are Q values that are reasonably closer to each other.
So now that there are a lot of empty
Yeah. Yeah. Most of them are 0. Yeah. In fact, if you remember, instead, when we had a easier environment, here, let's keep it quick. The 10 episodes that we visualize at the end are always with the same path. Okay. This is more or less the same difference that is in training and testing with usual supervised machine learning. No? So here what we did is we train. At the very end of training, we take the Q table that actually is the policy. We take the policy, we save it, and then we use that same policy for, in this case, 10 times without exploration. So without ever choosing the exploration action, but always sticking to the Q table. And let's say, in scenarios that are solved, so where the optimal policy, whatever it is, has been discovered, you can find that the path followed is always the same. For instance, if you want, for instance, I don't know, to see what is the chance of, even at the end of training, what is the chance, if you want to keep a small chance to do the random action, here in the parameter test, you put false. And then basically you keep the exploration, I don't remember actually, but I think you keep the last epsilon that you got in training. It should be. So in this case, we can see not always the same path because the agent still has 0.05 chance of doing something else. Have you seen that it goes back to the starting position for a bit? Yes?
The parameter runs is at 1.
Now it's 1.
And with 3 runs, the output will be 3 times, every clock 3 times, or just 1?
No, should be just 1 at the end. And the only thing that changes is that it will be more statistically significant because you did 3 different runs of the same experiment. Okay, we can try in an easy scenario. If I didn't mess up anything, it should be only 1 plot average over the different runs. But let's check. Maybe I did mess up. Could be. So this should be quick enough even if we do 3 runs. So first run, second run, third run, and yeah, one plot. So simply here the results that you got are more statistically significant because you got more samples, 3 times the data that we had before.
Based on the average?
No, here I think I did it quick, so it's the last Q table. Yeah, I think I did it quick, it's the last one. And yeah, even in this case, the agent can mess up because we kept a bit of exploration. Okay. Why would you keep some exploration even if you learned the optimal policy? Well, it depends. In this case, the optimal policy is deterministic policy. Not in every environment the optimal policy is deterministic. If you have a probabilistic policy, so it is not always the case that in that state that action is the optimal. Well, in that case, it makes sense to keep a bit of exploration. And basically that's it. As I said, you can test, we can do the last test maybe, so the slippery part. So let's see the parameters. Let's keep 3 runs since it's quick enough. Now if you activate the slippery parameter, things get really messy. With messy, I mean it becomes very difficult to do some guessing. Because actually, we will mention this more in the multi-agent part, you change your Markov decision process. It's not anymore a Markov decision process, it's a partially observable Markov, becomes a partially observable Markov decision process. So can you see here that the elf moves even when facing a different direction? That's the slippery part. So the agent is sort of drifting, okay, in the snow. And this time it went actually good. So it learned the good policy. But it again messy. You can see for sure that the line is much less smoother than before. It is very messy. And now that I see the behavior of the agent, it may be the case that actually slippery is implemented in a different way. The agent at any point in time could change the direction it is facing. So you need to understand, okay, I don't need to go down, I need to go left to go down. It could be implemented that way. This depends obviously on the environment that is taken from a library. Okay, so you read the documentation and you understand. But as you can see, it's much more messy, okay, learning. And this again, let's say that this is the only crucial change we did to the parameters. We completely changed the problem formulation. We are no longer in a Markov decision process, we are in a partial observable Markov decision process. Let's try to remember what does it mean, because we only mentioned this in the very beginning. In a partial observable Markov decision process, the agent does not get the true state of the environment. It gets any kind of approximation of it. Could be, instead of seeing the whole grid, I only see a portion of the grid. Or, as in this case, there can be noise in the actions or in the observation. So the fact that the ground is slippery, again, I will need to double check the environment documentation, but it could mean either that my actions are noisy, so I say go down, but I actually drift, or it may be that my observations are noisy. I think I'm facing one direction, but I'm facing another one. Okay? So basically, in a partial observable decision process, the difference is the reason why here I put observation and not state. In general, the agent has some observation of the environment, which doesn't mean it can see the whole environment. Whole intended as all details of the environment. It's easier to understand with the examples that we did last time. So for instance, if you have a robot with a camera, you can perceive an approximation of the actual environment, what the camera can give you. So a given range, you cannot see behind obstacles, the resolution may be not top quality, whatever. If you have a leader, maybe you have a leader in the 4 directions, so you don't see in the diagram. That's a partial observable. The state of the environment, the position of the robot, the position of the obstacles, cannot completely be perceived by the agent. And this is most of the time the case in real-world scenarios. So you only have an observation function that takes the environment state and outputs a subset of the environment state for the agent to see. That's the most common case in real-world scenarios. All of the other changes to the parameters were either increasing the difficulty, decreasing the difficulty, stuff like that, but they were not actually changing the formulation of the environment. So again, as I said, the code is in this new repository. A few commands you can run to run the code, and some experiments to do. So now actually we come to the actual overview of what multi-agent reinforcement learning is. So first of all, we need to, obviously this introduction of RL is not at all exhaustive. So there are nowadays many algorithms for single agent reinforcement learning. We only stick with Markov decision processes, but partially observable Markov decision processes will deserve some explanation. Already, single agent reinforcement learning can be divided in several subfields. Model-free reinforcement learning, the one we focus, so we don't care about understanding how the environment works. We only care about understanding what the best policy is. But then there is model-based reinforcement learning. So no, let me first try to understand how the environment behaves. So try to understand, to reconstruct the Markov decision process. And then when I have it, basically I can use dynamic programming. So the learning part is limited to the learning how the environment works. Obviously obviously you can have several different formulations of the environment. Usually they stem from beam theory, and usually you can have many algorithms, many families of algorithms. You can have on policy learning, so the policy you are optimizing is the same you are using, like original source. Off policy, like learning. I am optimizing a policy, I want to improve a policy, but the policy I use to actually learn is a bit different. There is an exploration part. You can even do offline reinforcement learning. So somebody at some point said that running simulation is expensive. Sometimes you can collect data and then run algorithms on that data. So offline reinforcement learning is more similar to traditionally supervised learning. You have a dataset, you run your algorithms, and you try to see whether what you learned actually generalizes to the actual environment. Just to give a brief overview, then there are lots of other variations of reinforcement learning. So now let's try to understand what happens when we move to the multi-agent setting. Conceptually, it's very easy. The only change is that now we have multiple agents in the environment. So the picture that, if you remember, we have seen at the very beginning is now made like this. We have multiple agents, each with their own action, each with their own observation and reward. In the most general case, agents can be different. I can have a movable robot, a fixed robot, a robot that moves on wheels, a robot that moves on not on wheels but on legs. Okay, so agents can be different. In the more general case, they can have different actions, they can have different observations capabilities. Even if the agents are homogeneous, most of the literature is about homogeneous agents, so they are all the same. Not meaning that they need to use the same learning algorithm, but they are all the same in the sense that they see the same things and they act in the same ways. But for instance, the reward can be different. Maybe you have one reward function, but the reward function gives rewards to the agents different, depending on what they did or something like that. So the novelty in multi-agent environment stems from the fact that what changes the environment, the state of the environment, is not the action of a single agent, but is the combination of the actions. So what is called in the literature the joint action. And what the agents can see about the environment usually is different. Each agent usually can see a portion of their environment. And so, for instance, if they would like to build the whole environment state, they will need somehow to collaborate, to exchange their own perceptions. So, first of all, why multi-agent reinforcement learning? So, why don't stick with single-agent reinforcement learning? Well, there are a few motivations. So first of all, why taking a reinforcement learning problem and turning it into a multi-agent learning problem? Why this may be worth? It could be that the problem is too hard and you need multiple agents to deal with it. Okay? This could be the case. Simply the state space is so huge, the problem, the solution landscape is so huge, you need to deploy actually more agents and try to make them collaborate. It could be that centralization is unfeasible. So in my domain, it is completely unfeasible to think about having one single software controller that decides what to do. It's, I don't know, the system is geographically distributed, there are connectivity issues, whatever, so I need to deploy more agents. Obviously, we can also have the constraint that stem from the domain. If I want, by design, independent robots, I need to devise out a different controller for each of them. Okay. Also, there are motivations stemming from the reinforcement learning part. So, for instance, if for a given goal, it is not so easy to check, to establish a priori what the optimal policy is, it may be the case to deploy again multiple agents and see which one gets to the optimal policy or what are the differences between their own performances. If the environment is partially unknown at the same time, this makes sense to deploy more agents to explore better the environment. And also, obviously, if we have a multi-agent system, we may want to introduce reinforcement learning because it is impossible to enumerate all the situations the agent can face. Okay, so these are basically motivations for why from a single agent reinforcement learning algorithm would I want to go to multi-agent? For instance, for these reasons. And instead, why, if I have a multi-agent system, may I want to include reinforcement learning techniques within it? These motivations. Okay. When you go multi-agent, by design, you need to you don't need to, but it is highly likely that you need some basic knowledge of game theory. Because game theory is the field that traditionally studied interactions between different agents. Okay, so as I probably already anticipated, multi-agent reinforcement learning started regardless of game theory, started as a branch of single agent reinforcement learning or multi-agent system. Then after some time somebody recognized that actually it was meaningful to be knowledgeable about game theory literature. So we will see that there are strong bonds with game theory and that some of the notions have been taken by multi-agent reinforcement learning. Reinforcement learning is not the only technique that can be applied to multi-agent systems to make them learn something. This is just to tell you that that's not the only technique. Evolutionary computation is a huge family of approaches to inject some sort of learning in a multi-agent system, and also sort of intelligence. So evolutionary computation is a family of algorithms loosely inspired to the theory of evolution, and swarm intelligence instead is a family of algorithms loosely inspired to how insect societies behave. Okay, they are very fascinating. And there is a nice paper linked here that gives an overview. Why we focus on reinforcement learning? Well, first of all, because I work with it, and so I want you to collaborate with me in the future, okay? And the other reason is that reinforcement learning is a technique that naturally suits agent systems, so systems in which the idea of having different software controllers is already there. Simply because reinforcement learning, as we said, works by trial and error. So agents need to interact with the world, do actions on the world, perceive situation, and stuff like that. So that's a perfect match. Usually, in fact, in multi-agent systems, we assume each agent to be rational. So they do the most rational choice according to whatever utility function. So for instance, the policies that the agents adopt or learn are based on a utility, so the reward, for instance. In multi-agent systems, usually agents are situated, means that they live in an environment. It can be not a physical environment, but a virtual environment, okay, it's fine. But they live in the environment, so they need to check what the situation in the environment is, and then decide an action accordingly, and do that action. This is called usually situatedness in agentic systems theory. And usually, in multi-agent systems, the agent is said to be autonomous, which means that the agent makes its own decisions according to its own utility, and other agents cannot interfere. Okay? So they are, let's say, almost a perfect fit. That's one reason. Is it actually applied, multi-agent reinforcement learning? Yes, as I said, it's much more in the early stages with respect to reinforcement learning, but obviously I would say that even reinforcement learning is something you find in any kind of company, only some companies. But multi-agent reinforcement learning already proved to be effective in several scenarios. So here are just a few of them, the most widely used. So any kind of robotic environment. Okay, in robotics, obviously, reinforcement learning is a huge player, simply because completely hard coding a robot is very difficult. Okay, foreseeing every possible situation that the robot can face, every small deviation in the actual physical environment is very difficult. So for instance, learning optimal paths, learning to place items, learning to navigate scenarios, something like that. Obviously video games, for the, let's say, the brain of the automatic characters. In autonomous driving, okay, nowadays that semi-autonomous driving is more or less a reality, in some parts of the world at least. Maybe sometimes you read some news about, I don't know, Waymo vehicles that blocked an intersection because they were all waiting for something, stuff like that. This is a multi-agent problem. So there are multiple agents that have been trained with reinforcement learning also to learn some policy. But when you put more of those agents, and we will see why, when you put more of those agents together, they can fail arbitrarily badly. And that's why, that's because you didn't account for multi-agent part of the problem when you were doing reinforcement learning. Automatic trading in finance, recommendation systems are those systems similar to when you buy something on Amazon, and Amazon tells you customers who bought that also purchased this other item. That is more or less what a recommendation system is. So just to keep you awake and interested, here are a few examples. So this is a simulator for autonomous driving. In this specific scenario, the task is to keep driving in a highway despite other obstacles. This is a competition that is traditional. It is many years that this competition is run in different conferences, so robotic soccer. And this was a paper that was very nice, mostly because of the visualizations, by OpenAI a few years ago. Here basically you have two teams of agents. So within a team, agents collaborate because they are teammates, and in different teams, obviously, instead they compete because they are enemies. And this is basically an evolved form of hide and seek. So blue agents have the goal of hiding from the red ones. The red ones must instead seek for the blue agents. And when the red agents have in line of sight a blue agent, they win, and the blue agent loses. Okay? One nice property, the main reason why this paper was very, very famous, very nice, was that all the behaviors that you can see, so the agents that start moving boxes to block doors, the adversaries that use ramps to climb on top of the blocks and so avoid the obstacles, all these kind of building shelters, okay. All of these kind of behaviors were appeared by emergence, which means there were no direct incentives in the reward function to the agents to use those items. The reward function only rewarded, was sparse reward, so only rewarded which team won, the blue team or the red team. By running this thing for many times, okay, we're talking about OpenAI, so billions of episodes for billions of instances of the environment in parallel, the agent eventually, in a completely autonomous way, learned to exploit these objects in the environment at their own advantage. That was very striking because, again, with no whatsoever direct incentives, they learned what to do with the items in the environment. Okay, and that's very nice, very interesting. Okay, nice, wonderful. those videos were wonderful. Let's do multi-agent reinforcement learning. Okay, I agree, it's wonderful, it's very difficult. Even if conceptually the only thing that changed is that we put multiple agents in the same environment, this has lots of consequences. And we will now examine the most macro ones that are three main consequences. So, when you go from one agent to multiple agents, immediately your decision problem becomes non-stationary, by definition. If you remember, what does it mean, stationarity, which was one of the underlying assumptions of Markov decision process, okay, and also of partially observable Markov decision process. Whatever the environment transitions are, they do not change over time. They are fixed. Why now I say that as soon as you put more than one agent in a shared environment, no matter what the environment is, the environment becomes non-stationary. Simply because what one of the agent does, sorry, not one of the agent does, the consequence of the actions of one of the agent no longer depends only on the state of the environment. They depend also on what the other agent is doing. Let's imagine, for instance, in the previous case, that two blue agents try to pull a box, and they pull in different directions, the box doesn't move. If only one agent pulls, the box moves. So the environment transitions, the change induced in the environment by my action, changes in time. It depends on what another agent is doing. So, any multi-agent reinforcement learning problem cannot be a Markov decision process, by definition. That's a huge difference. Why? Let's be a bit more precise. As we said, in single-agent reinforcement learning, the state transition of the environment depends only on the dynamics of the environment and on the actions of the only existing agent. That's it. In multi-agent reinforcement learning, the environment is shared. So each agent actions affect what the other agents see and the state of the environment. So the environment transition may change over time, and this means, as a consequence, or these are all corollaries, if you want, to this change. If this environment state transition changes during time, it means that the optimal policy that the agent is seeking may change over time. If the other agent is, I don't know, wandering randomly in the environment, my optimal policy is to pick the box and pull the box somewhere. If the other agent is doing the same thing, my optimal policy could be do nothing, or push in the same direction he is pulling. So, I have a different optimal policy depending on the policy of another agent. That's something that is not present in reinforcement learning. This causes a problem which is called the moving target problem. So, the agent has a target, has a policy that is not fixed. In the frozen lake example, the policy, the set of equivalently optimal policies were fixed. Now it is not fixed anymore. Let's assume that you put in that environment, the frozen lake, and that could be a nice exercise because it's quite simple. Let's assume to put another agent, even with the same goal, to achieve the goal. But agents may collide, so they cannot occupy the same tile. Okay? They collide. The environment becomes non-stationary. If I want to go right, but on the right I have the other agent, I cannot go right. Okay? So, my optimal policy depends on the other agent. One real-life example, I don't know actually to translate it in English, but it's the corridor cross. I guess it happened to you at least once to be walking on the side of the road, on the walk side, and there is another person incoming. Okay, the sidewalk is very thin, it's very narrow, and so you start dancing. No, okay, I go left, no, he goes left, no, I go right. Okay. That's the classical moving target exemplification. My optimal policy depends on what he's doing. If he goes right, I also go right. If I go left, I didn't change anything. Okay, so that's the classical problem of the classical exemplification of a moving title problem. So first issue, the environment is no longer stationary. Second issue, in a single agent setting, if the agent achieves the goal, who is to award, because the responsibility for the agent to achieving the goal can be attributed to that entity. The agent is the only one that is acting in the environment. If the agent achieves the goal, okay, good for the agent. He was a good boy. If you are in a multi-agent scenario, who is to give credit for when a goal is achieved? Every agent? Only some? Every agent, but not equally. So again, you have two little elves in the frozen lake scenario. To get a reward, they both need to achieve the goal. Let's assume. So, if an agent achieves its own goal and the other doesn't, who is to blame for and who is to award? One is to award, obviously, the other is to blame. So the reward function needs to change to account for this. Okay? Or if you are in a robotic warehouse environment, I have moving robots that need to transport items. Maybe there are some heavy items that need more than one robot to be carried over. If I grab one of these items, and then I start pulling towards the delivery zone, and another robot picks up the item, but pulls toward another direction, who is to blame for and who is to award? So, the problem is assigning responsibility for good or bad outcomes. In single agent enforcement learning, there is only one agent in the environment. So the actions that contributed positively or negatively to the goal are the actions of that only agent by design. When we have multiple agents in the same environment and they act together simultaneously, what are the actions that contributed positively? What are the actions that contributed negatively? What are the actions that were completely useless? So, this is called a credit assignment problem. It exists also in a single agent learning regime. We didn't mention it, but in a single agent world, the credit assignment problem is a temporal problem. Along the path toward the goal, what are the actions that were good and what are the actions that were bad? That's the temporal credit assignment. This exists in a single agent case. But in a multi-agent case, it exists another credit assignment. Which agent to blame or congratulate to? And the most, I guess, intuitive example of this in the real life is a group project. Somebody happens that you do a group project and somebody's not doing anything and you carry them over. And maybe at the end of the project they also get a good grade. That's it. So that's a credit assignment problem. In that case, the teacher faces this problem. How can I measure how each of the components of the group contributed to the project? It's not a trivial task. The last, which is a bit more involved, it will probably become a bit more clear afterwards, is in a single agent environment, the reward that the agent gets by doing an action in a given state is always the same. Okay, this is a bit of an approximation because we said that the reward function itself can be stochastic, so it is not actually like this. This is a simplification. We should say that the reward is stationary, like the environment. So the probability distribution doesn't change over time. But just to be clear, let's assume that, like in frozen lake, the reward is fixed. It does not change over time. So as we said in the very few early slides, in single agent reinforcement learning, the learning goal is always the same: maximize the expected return. Then this may translate to achieve the goal, kill the enemy, depending on the specific problem, specific environment. But in the mathematical representation of the problem, the goal for the only living agent is always to maximize the expected return. That's it. That's not the case in a multi-agent system. In a multi-agent system, since each agent action may affect each other, observation and also action, each agent can get a different route. This may happen. Okay? So this means that the expected returns for the different agents can be different, depending on the policy they are actually using. And even if you run the same experiment, the same exact policy for all of the agents in the same exact way, the returns can be different because they depend on the sequence of the policies, the environment state transition, dynamics, whatever. So maximizing the expected return is no longer well defined. Maximizing the expected return of whom? All of the agents? A given subset of the agents? It is not anymore well defined what maximizing the expected return means. And this may depend on the actual environment or on the kind of solution you want. Let's go back to the example of the intersection, of the traffic intersection. As we said, maximizing the throughput of the intersection, or maximizing, let's say, maximizing the return. Let's assume that we have multiple agents with different intersections, or we have multiple agents in the same intersection, each facing a different direction, so each controlling one side. If we simply transpose the single agent setting, so each agent wants to maximize its own reward, we may end up with a case in which everybody is fighting, everybody wants to go green light, and every car crashes. Or if you have multiple agents in different intersections, it does not make sense for an agent to give the green light if the agent in the intersection after himself has the red light, because I will start to form a queue. So whenever you have a multi-agent system, it is not the case that you necessarily want every agent to achieve the maximum possible expected return. Sometimes you may want at least one agent to get the maximum return. Or you want all agents to get comparable rewards. It depends. It depends on the kind of problem, on the kind of solution do you want. So, we will see that when defining the multi-agent reinforcement learning problem, we do not need only to define the problem, so the Markov decision problem, the environment, like we did in single agent, but we also need to define the solution. Which kind of properties do we want from our solution? Something that in reinforcement learning we didn't do. The solution was simply to maximize the expected return. And here is where most of the game theory comes into play. Because in game theory, the issue of studying the different equilibria between different agent policies is one of the core businesses in game theory. So let's actually clarify a bit the terminology. This will be useful mostly if you, for some reason, read papers on the subject. Because basically, depending on the background, on the area where the paper has been published, or the background of the writers, you can hear different terms. So again, as we said, multi-agent reinforcement learning and game theory is deeply related, because both are about studying interactions between different agents, okay? We could try to draw a rough distinction between the two, but this distinction is more and more blurred the more the research advances, okay? Because now the fields are really emerging. myself when I approached reinforcement learning and then started studying multi-agent reinforcement learning, in my I'm old, so in my studies I didn't really have any full lecture about game theory. I needed to study something because in every paper I read, one every 4 terms was something from game theory. So, if we wanted to draw at least an historical distinction, game theory was mostly developed as a mathematical economic theory. Okay? It was mostly focused on competitive scenarios. And the emphasis was on provable properties of the solution, so the Nash equilibrium, stuff like that. Okay, so traditionally, game theory dealt with two agents, okay, which were adversarial, and studying the strategic interactions for each agent to get the most of its own utility function. Traditionally, nowadays it does lots of things. Multi-agent reinforcement learning instead was mostly developed in a research field huge that is called distributed artificial intelligence, at the crossroads between distributed artificial intelligence and machine learning. So, the specific nature of the scenario did matter less. So whether the scenario was collaborative, competitive, or even mixed, okay, we need to do something different, but we don't really focus on one. Probably collaborative scenarios are a bit more focused, but not necessarily. But for sure, the emphasis here was to compute efficient solutions. So we don't really care too much about provable properties, but as soon as I have a reasonable solution, that's fine. Okay? And this is natural because even reinforcement learning usually is applied when there is no other solution not feasible. Okay? So the fact that these two fields, for a lot of years, I would say at least until 2018, something like that, were mostly separate, created a lot of terminology mismatch. So lots of papers that are mostly doing the same thing but with different terms. So just the very basics of clarifications. What usually in game theory is called the player, in reinforcement learning is called an agent. What usually in game theory is called the game, in reinforcement learning is called the environment. And we already know that even this terminology can be generalized. The decision process is the most general term. Both are about describing decision processes. In game theory, you have the payoff that is usually given by a payoff function or a utility function. In reinforcement learning, you have the reward. And what usually in reinforcement learning we call a policy, in game theory is called a strategy. So when you read about the player strategy is to, that's the agent policy. The match is 1-1. Some definitions apply to both, some definitions instead may differ. So for instance, one of the issues I had when starting to study these things some year ago was that basically you had two different papers that formulate the problem in two different ways, with two different names, and I have the feeling these problems are the same. And in fact, I was right, but it took a bit of work to understand that. So now, for instance, we define exemplary games, likewise we defined exemplary decision processes, the NDP and the PONDP. But now we talk about games simply because we imagine to be in the game theory field. But we can talk interchangeably about environments, about decision processes, they are the same. In fact, a game is defined as a model of multi-agent encounters in a given environment, which means with given rules. Okay, so it's an abstract model, like a decision process model. 3 examples of games with increasing complexity. Matrix games are the most basic games. All other games are defined as variations of this. Similarly to the Markov decision process in single agent reinforcement learning. That was the basics. You have multiple agents, but there is only one environment state. So it's a game that immediately finishes as soon as each agent acts. For instance, rock, paper, scissors. You drop your hand and the game is finished. There is no state actually. Okay? In this class of games, you can have zero-sum games that are games in which the different players are all adversaries. If I win, you or everybody else loses. We cannot both win. Okay? So any game, any competitive game is a zero-sum game. If I win, you lose. That's it. Common reward instead, so a zero-sum game is purely competitive, right? Or adversarial. A common reward game instead is purely cooperative. We all get the exact same reward. So either we win together or we lose together. And then there are general sum games, arbitrary rewards. Okay, I can get a higher reward, you can get a lower reward, another agent can get a reward similar to mine, whatever the case. If you extend, obviously these games are a bit trivial because there is only one state. So for instance, strictly speaking, a purely matrix game is not really of interest for reinforcement learning. Why? Because if there is only one state, there is no sequential decision making. I mean, it is not that I do an action, I end up in a different state, I do another action, so I need to do multiple decisions extended in time. I need one decision and I get to the outcome. Again, this doesn't mean that you cannot apply or study reinforcement learning in this case. It's simply a little less suited, okay? If you extend a matrix game with multiple states, for instance, tic-tac-toe, the game of 4, whatever game has an actual state, you are speaking about stochastic games. Why stochastics? Sometimes the choice of names is not really good. Then, one peculiarity of another dimension, let's say, that we barely touched is, usually in these games, agents are supposed to act simultaneously, concurrently, not in turns. Instead, if you have agents that act in turn, the formulation of the problem changes a bit. We talk about extensive form games. This is the classical way to model board games, for instance. Right? Usually you act in turn, a game of Monopoly, a game of whatever, you act in turn. So this is just an example to say that there are multiple aspects to consider in modeling a game. We just sample a few to give you a glimpse. So first of all, some examples of matrix game, the most basic one. Rock, paper, scissors is a zero-sum game. You have two players. If I win, you lose. We cannot win or both lose. We can draw at the very least. Then this is let's say a synthetic game. It has been conceived, it has been invented, so-called a coordination game. Usually the way you express in game theory the payoffs of the agent, so the rules in a sense of the game, is through tables, matrices, that's why they call matrix game. So for instance, here you can see the two players, the row player and the column player. If the row player drops rock and the column player drops rock, they draw. So they get a reward payoff of 0. If the row player drops rock and the column player drops paper, the row player gets -1, loses. The column player gets 1, wins. And the same here. In the coordination game, both players need to choose the same action. And then they get the reward. Instead, in a general sum game, and the most famous is the prisoner dilemma, I don't know if you encountered it somewhere. In the prisoner dilemma, the reward is completely arbitrary, the payoff. Did you know the prisoner dilemma? Well, the prisoner dilemma is very, very famous, so quick roundup. Because it is, let's say, the easiest example of a general sum game. So a whole class of very realistic games. I know that at first glance it may seem not like so how can this be a good abstraction of real world problems like pay taxes, deciding which portion of land to destinate for crops, so harvesting crops, animal grazing, or keeping as a wood or stuff like that. Deciding on fisheries seasons to not deplete the fish. All of these actual very real world problems can be modeled with a prisoner dilemma. So in the prisoner dilemma, you have two prisoners that have been arrested and for a crime, and they are interviewed in separate rooms. They cannot communicate. Usually in game theory, the agents cannot communicate for some reason. Mostly because it stems from competitive interaction, so you don't want really to communicate with your competitor. So they cannot communicate, separate rooms, as you see in any crime fiction on the TV, no? Separate rooms, separate interviewers. And the numbers that you see here are the number of years of prison they will save if they do something. So -1 will be, I can save 1 year of prison. Okay? The numbers can be arbitrary, so it doesn't necessarily need to be -1, -5, -3, but they need to respect certain proportions. So what does it mean, C and B? C stands for confess. Okay, so they confess, one prisoner confesses, okay, it was me. D stands for, I think, defect. So no, it wasn't me. Usually C is also translated with cooperate, because it's cooperation or defection. So, if both agents cooperate, so they both say, I confess, they save 1 year of prison. I don't know, the default is, I don't know, 7 years, I don't know. If one player defects, so it was not me, and this is not the years saved, this is the years of prison. So only 1 year of jail. If I defect, I say it wasn't me, and the other one confesses, I don't go to jail. And the other one gets 5 years. If the interviewers have if the detectives have no clues, they can only rely on confessions. So. And obviously, this case is perfectly symmetric. No. If I confess and my partner defects, I go to jail for 5 years and he is free. So this case is completely symmetric. But if we both defect, it wasn't me, the detective have enough evidence that either one or both of us did the crime, we both go to jail for 3 years. Okay? So the most important thing is whatever the numbers, this should be the low, the 0 should be the lowest, then this, then the 5. Then you can scale numbers as you wish. Okay? This is a very interesting problem. Why? And then we go on with our slides. According to game theory, agents cannot communicate. Agents play the game only once because they are interviewed. At the end of the interview, you are either convicted or left free. The rational strategy, so if you pick any kind of algorithm that exists in game theory to devise out the most rational choice is to defect. And it's quite intuitive. If I defect, okay, the worst case scenario, so if I defect and the other confesses, he goes to jail for 5 years and I save jail. If I defect and the other defects, I go for 3 years. So the worst is 3 years. But instead, if I confess and the other does not confess, I go for 5 years. So the problem with most of the existing to date game theoretic solution were that they look only at the worst case scenario, like an engineer, right? Always look at the worst case. What is the problem? The problem is that this kind of rational behavior makes you blind to the fact that if you both confess, you get to jail for less years. So here the optimal strategy is not to defend, is to confess. And this is something that for a perfectly rational agent in this perfect setting is out of reach. The optimal choice, worst case scenario, is to defend. Obviously this was a big result. In fact, Steve Nash got a Nobel Prize. Okay. Examples instead of stochastic games. So matrix games with multiple states were video games. This is, for instance, cooperative Pong. So a version of the old Atari game where you should keep the ball alive, basically. You control two pads and the balls must keep alive. So this is fully cooperative. Or we have this another synthetic, let's say, environment that has been created especially to stress test cooperation. It is called level-based foraging. Basically, you have the agents that need to collect apples. But to collect apples, both the apples and the agents have a level. Each agent can only collect apples of his same level or lower. If agents want to collect apples of a higher level, they need to be both nearby the apple, so that their individual levels match the level of the apple. So this can, depending on some configuration, this game can be common reward or even general sum. This is just random samples, okay? There are many more game formulations that we don't see. So we mentioned similarities between game theory and multi-agent reinforcement learning. Obviously, there are also differences. That again, this difference, the more time passes, the more they are blurred. Okay, so let's take them with a bit of salt, with a grain of salt, meaning that these are mostly traditionally what the two fields did. So, in game theory, usually the environment only changes due to the actions of the agent. Otherwise, it's static. Instead, in multi-agent reinforcement learning, we are more open. The environment can have some sort of spontaneous transitions, okay? So, nobody did anything, but the environment changed. Could be. Another difference is that, traditionally again, in game theory, every agent knows the rule of the game. So, for instance, in the prisoner dilemma, the agent knows the payoff matrix. That's why they can compute the best strategy. They don't need to learn. Instead, as we know, in reinforcement learning, we assume usually minimal knowledge of the environment. Every piece of knowledge you have, you must justify it. So, usually the reward function is unknown. And in multi-agent reinforcement learning, not only the reward function is unknown, but even what specific number the other agent got is usually unknown from the perspective of each agent. The environment transitions are known, so again, this is the most striking difference. The rules of the game are unknown. What other agents can observe from the environment is usually unknown. I know what I can observe, not others. Same for the actions. In some cases, not even the number of the other agents is known. Okay, so we tend to assume minimal information, and this is just a hierarchy of the kind of games, exactly because sometimes these formalizations have been developed in those different fields. Okay, they are variations of each other. They can put them in relation. So, for instance, the two most basic kind of games we have seen for reinforcement learning and game theory were, respectively, the Markov decision process, one agent, any number of states, we don't care, and the matrix game, that is flipped, any number of agents, but only one state. So they are, in a sense, they are complementary, no? That's why it is natural that the two fields of research are converging. If you transition instead to a stochastic game, this is a more general class than both of them, because we can have both multiple agents and multiple states, but the common factor is that we assume full knowledge. Okay? Full knowledge only meaning the environment state. Okay? Okay, so we can observe the exact state of the environment. If we remove this, we go to a completely different fact. So a partial observable markov decision process is a markov decision process where the true state of the environment cannot be perceived. And if we extend this with any number of agents, so in a multi-agent world, but we restrict ourselves to common rewards or cooperative scenario, we call this formalization decentralized POMDPs. Bad name, I know, but that's it. If we want to get to the most general class, so any number of agents, any number of states, and partial observability, we get to the partial observable stochastic games, POSGs, and they are the root of the fact. Okay, any MDP is a simplified version of a POSG. There are many more games, okay? This is just the macro families, more or less, and how do they relate to each other. So, the names are simply derived, and the hierarchy are simply derived from which field studied that specific game first, basically. So, for instance, that POMDP have been born exactly because since game theory was mostly concerned with competitive scenarios, they were mostly focused on cooperative scenarios. An example of the complexity of a partial observable stochastic game is a video game such as StarCraft. StarCraft is a video game in which you have multiple units that fight with multiple enemy units. So you have multiple states of the environment, multiple agents, each unit only perceives a portion of the environment, and also the setting is mixed because you need to cooperate with your teammates, but you are an adversary of the opposite team. Obviously this is a video game, but the real world is full of these kind of scenarios, okay? These most general scenarios. And this kind of thing has become a sort of a reference test scenario for multi-agent reinforcement learning algorithm. So if you want to, for instance, if you want to create the new best multi-agent reinforcement learning algorithm, testing the algorithm on this game is a good benchmark. This way. The last big difference usually between game theory, so we had as big differences we had the dynamics of the environment, the observability of each agent, and the last one is the communication. Usually in game theory, agents do not communicate. Okay? For instance, in game theory, if agents need to communicate, that's a class of games for that, referential games. Usually in game theory, there is no communication. In multi-agent reinforcement learning, instead, the observation function could also include communications from other agents. Okay? This is more free, let's say, to design. And in fact, the different multi-agent reinforcement learning algorithms that have been proposed actually exploit communication in different ways. That's one of the differences. Okay? Likewise, the action space of agents could include communication actions. So, I pull this lever, or I send a message to another agent. Communication has a huge impact, obviously. This is quite intuitive. Okay? If you wanted to coordinate with a friend of yours in the best way possible, to meet at a given point, at a given location, the best way is to message him. If you remove the messaging option, it's more difficult. You can do something, a different form of communication. Let's assume that for whatever reason you cannot send messages, but you can share your position, like via WhatsApp. Better than nothing. Okay, you can still meet, but you can chase around. Direct communication will be more effective. If you cannot communicate at all, it becomes difficult. Okay, it becomes very difficult. So, communication is so crucial that it is basically it became a whole field of a subfield of research. And by any chance, this is also the field where I work the most, where I am most interested. So let's do now another pause. In this section, we only draw from game theory the formalization of the problem, of the environment. No? In the next part instead, we need to talk a bit about also the solutions. So the fact that we said it is not anymore to say we want to maximize reward. Maybe we want to achieve the Nash equilibrium. Maybe we want to achieve Pareto optimal policies, something like that. And now we will give a shallow overview of these concepts.